So thank you for attending our DataOps and Confluent event. Today we'll be talking about event streaming and stream processing and use cases it can solve. We'll work through practical examples of stream processing as well. The event is hosted by Akash from DataOps and dataengine and in collaboration with Inna and James from Confluent. I'll pass on to Akash to introduce DataOps.
Awesome. So hey, everyone. Thank you for attending the New Zealand DataOps Meetup. So today we're going to be talking about Confluent and just Kafka and the evolution of Kafka. I guess I thought I'd share a story because I've been on the Kafka journey for about 5 to 6 years plus with, through Telstra and Spark and Curious, and it's an amazing piece of tech, and I'm a big fan because we managed to do the impossible with Kafka. I guess is probably the key thing. So from event processing to streaming capability to location insights, that wasn't possible before. But even for energy companies, the ability to expose, through ksql operational analytics in near real time, which we did in New Zealand for customer, was quite amazing. So really, this is something that I'm quite interested in learning a lot more from James, but it's kind of something that I'm quite passionate about as a whole. Now, I'd like to introduce James and Inna from Confluent, and maybe James, do you want to give a quick intro before you get into the details?
Yeah, sure. So James Gollan, a staff solutions engineer at Confluent. So my role is basically to go around organizations and listen to the business problems that they're trying to solve, and map a technical solution to those problems. And the nature of Confluent is that we're a company that I suppose is based around Apache Kafka, which is an open source project. So those solutions typically will involve event streaming. And so, I also put on my bio that I'm a long-suffering Wallabies fan because I thought for a New Zealand crowd that might, I don't know, you may not be a kind of rugby crowd, but it's very, very hard to deal with that. So do you want to kick on or Akash, would you like me to start? Or?
Sorry, talking to myself again. So get straight into it, James. Yeah, you can kick it off. Thank you.
No worries. And look, we've got a sort of a manageable group here. So kind of happy to take questions midway if you like, or you can leave them to the end. I'll try to leave some time for questions. But the topic I wanted to talk about is something that's, I think it's been sort of like a fermenting in my mind. This idea of blurring those lines between operational and analytics data. I think that's kind of like a really interesting thing. And so I'm going to be talking about this as a way of introducing and demonstrating stream processing with ksqlDB. There's no assumption that you know what ksqlDB is. Hopefully, we'll explain that during the conversation. But to kick off, I guess we're going to cover sort of fast data and big data and kind of how we extract value from each of these concepts, if you like. Also introduce kind of like what is an event streaming platform. We'll go through a stream processing overview, so I'll kind of explain the concept of it, and then we'll actually look at a running ksqlDB application that is doing something which actually has been traditionally quite difficult, which is Customer 360 and that current state of a customer object, and that will be in the customer loyalty space. And I start with this slide, and we take a moment to have a look at the slide, and sort of like there is a sort of like it's kind of a sense of menace here. And once you've sort of like taken in this idea of this young child about to cross the road, we add in this question: would you cross that road with traffic information that was 5 minutes old? And I think this is a really nice way of just establishing the importance of fast data and the importance of having access to real-time data, because clearly the answer to this is no. And then you start to think, well, 4 minutes and no, 3 minutes, no. So at what point? It's probably a couple of seconds is the kind of like maybe even less than a second is the right answer here. And so just does establish this notion of kind of like fast real-time data being incredibly important in decisions that we make as individuals, but also as businesses. And so that leads to this kind of like, and I think this is a reasonably uncontentious kind of statement, that all other things being equal, real-time data beats slow data. If we can have the data in real time, there's not really a downside to it, but there's a lot of upsides. And so we're seeing this across all industries. Banking was certainly one of the first industries to take on event streaming, along with kind of like telcos and insurance companies. But what we see here is some of the use cases that real-time data enables. And some of these sort of like start talking to that theme of blurring that line between operational and analytics. So we kind of like look at real-time sensor diagnostics, ETA updates, things like fraud detection, personalization, recommendations. All of these things need to happen in real time to gain the most sort of like value out of them. But when you stop to think about them, they're not kind of like just reacting to an event. They're reacting to kind of like an analytics window where we're understanding the data in real time, but it is still over a set of data. We'll go into that in a little bit more detail. But when we start to think about big data has what we might consider kind of like a value curve. And so in this graph, we can see value is plotted here on the y-axis. And generally speaking, the value of that data increases as you have more of it, because you can make more meaningful kind of like predictions, and you can see trends that may not be visible with a smaller data set. And so that's kind of like, I think, a reasonably well understood kind of like, value curve. But when we introduce fast data, that curve is very different. And so fast data still has value on the y-axis, but time is on the x-axis. And in fact, as time increases, the value of that data decays very quickly. And so the time to get access to that data really determines how much value we can extract. And I think it's really nicely illustrated by the pedestrian crossing, where the 5 minutes old is basically useless in that context. Not from an analytics point of view. So there may be interesting things we can do with 5 minute old data from that crossing in terms of predicting traffic and those kinds of things. But in terms of an immediate decision, or what we might even consider an operational decision, that decays very quickly. And we're going to come back to this graph because generally organizations are either very good or getting good at this big data piece. So they've got a data warehouse and they're doing analytics and reporting, and that's kind of well understood. Concepts like data mesh are becoming important to address some of the failed projects. But fast data, and actually Akash and I were talking about this at the beginning, like, I mean, this is an emerging area of strategic importance for businesses. And that's the area where I suppose Confluent, and don't worry, this won't be a Confluent sales pitch, this is more about event streaming, but that's where kind of Kafka and Confluent sort of play in this fast data area. So event streaming as a concept, to understand it, I suppose we have to understand what an event is. An event is basically anything that happens in your business. And so we can see some examples of events here. So in transportation, like companies like Audi are doing this kind of connected cars where all the sensors in the cars are kind of like being monitored in real time and then being pushed up to central hubs. And then they're actually looking for, meaningful insights they can get. But it's very important that they can actually respond to the data in real time, or, like sometimes we say real time or near real time because the definition will vary across industries. But typically we're talking about sort of milliseconds to, a second sort of like latency, depending on the application. And so here we can see kind of like something like a sensor detecting kind of like low tire pressure. And so that will be actually recorded as what we consider an event. Now, an event, we also sort of like can term this a business fact. And that's kind of really important because events are very much a log of what happened, and they don't change. We never go back and change an event because it is actually an observation. And probably closest analogy would be to, a general ledger in bookkeeping, where you write something down. There's some, I think there's some term, accountants don't use pencils or something like that, where everything that you write in that ledger stays. If you have to do a correction, you do that as a follow-up entry. So it's really important to understand that events are kind of like logged, and Kafka really, a very convenient way of thinking about it is as a distributed event log. So other areas where we see events, like, as I said, like banking is big. So things like an account transaction where we're recording an account transaction, and in retail. So a lot of retail organizations are using events to track everything from point of sale to inventory to kind of like where customers are in the car park, so they can do sort of like click to curb or whatever, click to boot, and so all of those kinds of use cases are being used. There's another interesting aspect of event streaming, which is in an integration space. And again, Akash and I were just talking about this. A lot of organizations have an architecture which looks something like this. So we have a lot of applications and a lot of kind of like different databases and SaaS applications and a lot of point-to-point integration. And typically we can see here a data warehouse. Quite often the way that we're getting our data into a data warehouse is via some kind of ETL process that is point-to-point. And not generally reused. Now, with this slide, I try to sort of like, when you're actually talking to, I suppose, people who have been in this industry for a long time, they've seen this slide before. They would have seen it when they were buying like an ESB or kind of like an ETL solution, and they'd kind of like even know, they'd be able to predict the next slide is something like this, right? Which is everything's cleaned up by putting product X in the middle. And I think, though, there is a defensibility to this slide because this notion of the immutable stream of facts, centralizing the storage of those events, is actually capturing the history of the business. And it's opening up kind of like different integration patterns, which we will look at like briefly. Now I'm coming back to this kind of like this curve. Like, again, more than happy to take any questions, but like, I'm also very happy to just keep going.
James,
yeah.
Question from my side is, do you know the previous diagram? If you go back to it, the messy diagram, the spaghetti junction, I guess.
Spaghetti.
If you look at Auckland.
Oh, sorry, the previous one. Yeah.
Yep.
Yeah.
Now, Excel spreadsheets, that seems to be an ETL vehicle. It seems to be an analytical vehicle. It's a data science vehicle. Maybe good to understand how that fits into your integration patterns as a whole, because we're finding a lot of customers use Excel spreadsheets as a workaround or CSVs as a workaround. That
is kind of awesome, because the demo that I prepared has 3 data sources, and one of them is a CSV.
Perfect.
So
okay.
yeah, we'll take a look at that, and we can dig into kind of like pull back the curtain and see how that works. Yep. Yeah, so like, back to this value curve. And so, like, as I said, like many organizations kind of like are collecting this big data, but it's in that point-to-point way where they're offloading from an operational data store, pushing it into a data warehouse. And so they're extracting the big data value, but they're not extracting this kind of like fast data value necessarily. And so the way sort of like this pattern emerges is that we've got our kind of like data sources, and rather than actually integrate them directly into that data warehouse, the integration happens into Kafka. And so that integration typically is in the form of events, and there are different ways that we do that when we're integrating a database, but typically it might be change data capture. Of course, there can be SaaS services up here and kind of like other services coming into Kafka, but essentially we're converting every state mutation in the database into an event in Kafka and storing that in the immutable log. And the way we do that, again, there are different ways, but like, I mean, the most convenient way of integrating a known data source is using Kafka Connect, which is a framework that handles kind of like all of the complexities of integrating two systems and sort of like retry logic and delivery semantics, like exactly once or at least once and that kind of thing. And so by pushing the data into Kafka first, it allows us to extract this fast data, and then we can use Connect to actually sync that data into the data warehouse. So the end result is we're still getting data into the data warehouse, but what we've done is added a layer that allows us to extract this kind of like this fast data. Now, if you look at this diagram, kind of like, well, what are we actually adding here? Because we've just got a layer between systems and data warehouse. Well, we're adding this ability to actually process these events in real time. And that's what this talk is going to be discussing. So not only is the data flowing through Kafka, but it allows us to do what we call stream processing. And I'm going to give a more thorough explanation of stream processing in a moment. But it also, and a really misunderstood or poorly understood area of Kafka, is Kafka also allows you to store those events. And by default, that might be 7 days. But that can be 30 days, it can be a year, it can be 2 years, it can be infinite. So there's a separation of compute and storage with Kafka, where you can expand your storage independently of your compute and brokers. And that's really important, because when we think about the types of events, that raw business data, that's the unfiltered, unopinionated view of what happened in the business. So if we can store those events, we're not storing maybe a more opinionated idea of those events that has been transformed in some way by somebody for some reason, and then has lost a bit of the fidelity of actually what happened. So kind of important point with Kafka. But the other thing is, like, I mean, this looks like pretty much a linear pipeline. Okay, well, it comes in from operational, it goes through fast into big data, but big data is actually just one use case for a company's data. It's a very important use case, but it really is just one use case. And so we can see Kafka sitting in between not just the data warehouse, but other systems. And so microservices is a good example. The communication between microservices being event-driven is very powerful. But also we can be pushing into multi-cloud environments. And when we bring on new use cases, we can be integrating them via Kafka as well. So the idea that the data warehouse is kind of like the objective. It is one objective, but Kafka basically abstracts the data from the final destination. And that's where it's sort of like a little bit different from a message queue. Because we've got this infinite storage, message queues typically see data as being ephemeral. Its job is to deliver it from one point to another, whereas Kafka actually thinks of its job as being kind of this immutable log of what happened in the business. When we want to use that data, we then grab it and modify it in whatever way that makes sense for the downstream application. So I think at that point, yeah, so like we flick over to kind of like I suppose a quick whiteboard on just understanding stream processing. And but I'll pause there. Any other questions or just keep going?
James, there was a question from Greg. Was going to throw GraphQL in the mix from integration and front-end perspective be cool if GraphQL works with Kafka?
Yeah, great question. And probably an important thing to understand is kind of like the role Kafka plays, because typically what the role Kafka will play in that situation is it will be preparing the data using stream processing potentially, and then syncing that into a data store, which is then exposed via a GraphQL API. So Kafka is not kind of a replacement for an operational database. but it's a real enhancement to the way you build event-sourced applications using that data. Probably not a great answer, but maybe if I draw it out, it'll make a bit more sense. So like looking at that sort of like that idea and starting kind of like with stream processing, but to understand stream processing, we just need to delve a little bit more into Kafka. And so one of the kind of like most typical use cases is this idea of some kind of application, quite often a monolith, but can also be a microservice, and that will typically have a data store associated with it. And then you'll have a user who is kind of like interacting with that data store, and each of those interactions may result in a state mutation. Now, and chances are you will have kind of like more than one of these applications across an organization. So there'll be 3, 4, 10 data systems, and these can often become data silos. And one of the initial kind of like, I suppose, objectives is to actually get this data in a place where we can analyze it and report on it. And so this typically looks like some downstream kind of like data warehouse. And we might have, as I said, those ETL or ELT pipelines between those systems into that data warehouse. When we add Kafka to the mix, it changes a little bit. And so if I can just duplicate this out so we can actually understand how it changes. Yep, and we'll grab the database as well. So like we still have these operational systems, but we add Kafka into the mix. And so Kafka in this case is going to be represented here as this kind of like tube. And we start by adding kind of connectors into these sources. And these connectors basically speak to a particular flavor of technology on one side, they speak to Kafka on the other. So they're listening to changes in the database, and then they're actually capturing those as events, and they're pushing them into Kafka as a stream of events, just like the previous diagram we saw. And so we might kind of like have those events coming through here, and then we've got kind of like other events which are coming through and being stored in another topic. And then the way we get that data out is kind of like the reverse. So we have another connector here which speaks to Kafka on one side, and then is speaking to the flavor of data warehouse. And so we're going to look at an example of, say, DynamoDB, or, you know, like, I mean, as an output. And so like that's how that pattern works. And I suppose looking back at that whole integration idea, the really nice thing is we can repeat this pattern because Kafka is now acting as an abstraction between your source systems, which you offload the data from once, and now other systems. And so this one, obviously, we've got this kind of like analytics reporting workload. But let's say our data, we wanted to explore relationships between the data. It's still the same data, but now we actually want to understand kind of like, well, how things are related through other objects. And so for that, we might be using a graph database. And so we would actually grab the same events, but we would process them in a way that actually sort of like this might be kind of like Neo4j or something like that. Process them and store them in a system that actually is optimized for the kind of work we want to do on that data. And of course, there are other use cases. So like if I draw out an S3 bucket here, we might be syncing into S3, and that might be a compliance use case, all right? And so that's kind of like how Kafka addresses that integration piece. But what's most important for this conversation is stream processing, all right? So if you look at this model as it stands, data is coming in from a source system, and then it's kind of like it's just moving through, and it's getting to kind of like these destination systems in an unmodified, unaltered way. And we'll see kind of like in the demo that that's not always kind of like what the most desirable. And so stream processing allows us to actually modify those events in real time. And so stream processing as a concept is fairly easy to understand. So if we imagine that these lines are topics, A stream processor will essentially consume from a topic. So it will listen for new events in a topic. It will do some kind of processing. And then it actually creates events to a new topic. Okay, so this is the core of stream processing. Now, you might think, well, why doesn't it just modify the events in place? And that's because, as I said, they're immutable. They never change. They're business facts. You don't want to change those facts because they represent the most sort of like pure source document as to what happened. So this pattern is very common in event streaming, where we actually create new topics, and those topics then get pushed back into Kafka to be distributed further downstream. So that's stream processing. There's two kind of like, well, there's a number of stream processing engines, but in the Kafka space, typically we're looking at either ksstreams or ksqlDB. And today we're going to be looking at ksqlDB. Now, fun fact, ksqlDB applications actually compile down to kstreams applications. So kstreams is a higher level kind of like programming interface for streaming applications. The reason it exists really is because kstreams, you need to build this in Java. You need to compile it and deploy it as you would a Java application. Whereas ksqlDB is very much a SQL-like interface. So it's more accessible to more people. But it's also, it doesn't require you to actually deploy and manage the life cycle of an application. It allows you just to write something in an editor and deploy it via REST, etc. So, they're the kind of two options. This is kind of like the, I suppose, easier way to get started. Kstreams enables more complex use cases, but ksqlDB actually enables a lot of the common use cases that people try to achieve. And so they're the tools for stream processing. But in terms of, well, what can you do with stream processing? There's kind of like a number of things. And they start with the relatively simple, starting with kind of just filtering. And so filtering, as you might guess, like is the ability to just essentially drop events that don't match particular criteria. And then we're creating a new subset of the original topic in a new topic. Sounds trivial, kind of is trivial in terms of how you would build this, but it can have profound impact. The most, I suppose, powerful example is in sort of like a cybersecurity space where there are certain noisy events that aren't worth pushing into a SIEM, but without being able to filter in real time, you really have to push all of these events. And that kind of costs a lot of money because you're charged by kind of like throughput. So being able to filter out the noisy events, you can actually get kind of like a better signal to noise ratio at the same time as saving money. So that's the sort of like first one. The next one, which is kind of like we're going to look at and is pretty common, is just transforming the event. So this is changing the shape of the event. And so in this case, we might get kind of like a data package which has a very kind of like unfriendly structure, and it may have a lot of additional fields that are useful in a sort of domain-specific way, but maybe not useful more broadly across the organization. And if we want to share this event across the organization, we might want to use kind of like some kind of transformation logic to clean up that data object. And so this really starts to talk to things like, I suppose, data mesh, where data may be considered a product. And one of the things that does is it increases our focus on the shape of that data and the usability of that data, because now it's a product. I have customers. They need to be delighted by my product. And so it needs to be presented in a sort of like meaningful, consumable, easy to understand way. So transformation, a very kind of like common use case. The other thing that we can do is actually join. So I mentioned here kind of like that we have kind of like one or more upstream topics. And so the ability to join is actually really powerful. And so when we look at joining, a common example, and the one that we're going to see, might be you might have some kind of like fast data And so that's coming from maybe a sensor, maybe a smart meter. And so that smart meter is sending through a data packet, which is just an observation of kind of like electricity consumption over the last 5 minutes or whatever the window is, and a meter ID, right? And so that's coming through very quickly. But then we've got kind of like, I suppose, this kind of like slow data, which is, you know, information about that meter ID. So it's kind of like the more complete business object around the meter. And so that may include things like a postcode. And so by joining the fast data or enriching it with the slow data as it's processed, suddenly we have a better understanding of the data object itself. And we can do things like filter meter usage by postcode. So they're kind of like three, what we might consider stateless operations. So by stateless, I mean that each event is pretty much processed without any kind of like understanding of the context in which it exists. But an interesting thing about kind of like a flow of events is that they actually, when viewed individually, they will just be a particular business fact. But when viewed as a stream, which is basically an ongoing flow of events, the context actually leads to this idea of state. And it's actually pretty easy to kind of understand. So another topic here, and this time it's a shopping cart. And so each of these events represents a customer adding or removing something from a shopping cart. And so to simplify it, we might say we add something here, we add something here, we remove something, and we add something else. And so, you know, those individual events show that 2 items were added or 1 item was removed when sort of like viewed kind of like on its own. But when viewed over time, we can build up state. So if I start the state at the beginning, like the state of my shopping cart is 0. But if I look at the state at this point in time, it's 1, and then we get to 3, and then we're down to 2, and then we finish at 5. And so streams can actually be processed in a way that captures the state of that stream. And that becomes really important. And so like the, again, the example I show with loyalty points, we're going to be aggregating loyalty points. The other thing, and this kind of like really gets into that idea of blurring the line between operational and analytics. And the best use case, or the best example of this is fraud. And so we'll just say sort of like, you know, the stateful and sort of like, so we've got kind of like aggregation, average, etc. Also the ability to look at the most recent view of an object that's being updated via event sourcing. But stateful becomes really interesting when we start to add window semantics. So again, when you think about event streaming, you've got to remember that it's all over time. And so these events actually are ordered in terms of time, and we can place time windows around these events. And so if we imagine this topic represents credit card transactions, and this might represent, say, a 10-second window, we can write a query that is actually looking at a 10-second window and checking to see if the number of times we've seen a credit card number exceeds maybe 2. So what we're saying here is if I see the same credit card number presented 3 times in a transaction in a 10-second window, that's potentially problematic and potentially fraud. And so the pattern becomes this processor creates a new event. Remember, that's the pattern that we defined. But this topic may be considered fraud, right? And so this topic captures any event or sort of like the output of any of these windows that may indicate fraud. And then we have other systems, these operational systems that are listening to the fraud event to know whether or not they should do something. And so we might have kind of like a notification service that might be sending out a text message to a customer. So it's monitoring for fraud events. When it sees one, its job is to send out a text message. We might also have kind of like an account service that its job is to actually block an account or do further analysis or raise some alerts. And so this is kind of like very much an analytics workload, but it's a very short-term analytics workload that has an operational outcome. So the system is actually using these windows to tell other systems to do things. So that's where I think that we get a lot of blurring between those analytics workloads versus the operational workloads. Now, I'm not going to suggest that you no longer need kind of like a data warehouse. You absolutely still need a data warehouse. Data warehouse is absolutely perfect for kind of like, the bigger data operations, kind of like the more complex analytics and prediction, those kinds of things. And also for ad hoc queries. So you would never really want to use ksqlDB for data exploration beyond a certain point because it's just not the right tool for the job. So important to note that we're, talking in that way. So I think kind of like the next thing is to actually go into the use case and do a quick demo. But I'll pause there to see if there are kind of like any questions. I see there's, oh boy, we've just released a blog on GraphQL, so maybe my answer was wrong. I'm not sure. I'll have to read that. Thanks. Thanks for the link. Were there any questions on kind of like what we've covered or?
Hey, James. So this is Nitin here. Just on your last topic, the fraud transaction. Just out of curiosity, maybe it's a stupid question, but let's say if you're running some SQLs to analyze some fraud detection. So if it is event streaming, so how would you analyze each and every transaction? Like, is there any view or materialized view you have to create, and every time you have to update that view?
So the question is kind of like, how would you kind of like analyze that particular transaction in real time using stream? So that's a great question. And a stream processor, if we look at this kind of like this box here, that kind of can be anything, right? So typically it's sort of like, either, the modifications that I've talked about, but like a lot of customers use stream processing to implement some kind of, they might align it to a model server. So you might have some kind of like generated model that predicts or scores data. And the stream processor, as it receives an event, it passes that through to the model server, or it may even just be a class that's built into the stream processor. And it scores that data in kind of like real time or near real time, depending on the performance of the model server. And so it can actually use the scoring from that model to create downstream events. Does that make sense?
Yeah, good. Okay, thanks.
All right, so we might jump into the use case. Before we do, I'll just kind of like quickly describe what the use case is. So it's a customer loyalty application. The idea is that we've got kind of three types of data. So we start with the fast data, and that's kind of like, that's going to be point of sale data, right? So that's somebody swiping their credit card or a loyalty card or something like that at a vendor point of sale. And so we're expecting a lot of those transactions, right? And those to come through fairly quickly. But then we've got two other systems. So the next system, sorry, this is the loyalty points, right? That's very illegible. The next system is the customer system. So storing the customer profile. Right, and so this is actually being stored in this example. It's in a MySQL database, but it could be any kind of data store. And this keeps the customer profile. And we might consider this not fast data, but actually slow data, right? And so this data is fast. The customer data is slow. And we've got a third system, which is kind of like external credit reports from an agency, and they're provided as a CSV file. Okay, so in this case, we may even consider this to be batch data, where we receive these batches maybe only once every 30 days or something like that. And so the challenge from the business's perspective is we've got these three different flows of data, but how do we actually join these all together so that we can understand better a stateful view of our customer? So that's the challenge. So now I'm going to actually just jump into Confluent Cloud and
James, there's a few questions.
yeah.
So what is co-partitioning from Indrajit?
I'm not sure if I said co-partitioning. Partitioning is very important concept to understand in terms of topics. So each one of those sort of like lines that I've been drawing, so each one of these kind of like colored lines kind of represents a topic, okay? And there's an implementation detail of a topic, which is actually, a topic is really made up of partitions. Oh, sorry, okay, co-partitioning. So it's kind of complex. So ksqlDB operates as a distributed system. And so you'll have lots of nodes on potentially different data centers. And they need to join data. Now, it would be very expensive to actually go across the network to join on all of the different data, sort of like all the different instances of ksqlDB, because they'll all be handling a small subset of the data. So co-partitioning is kind of the process of getting, if I want to join on customer ID, it's getting all of the data into the same kind of like partition so that it's stored, partitioned in the same way so that it's stored on the same machine so that we can do kind of like this distributed query. Yeah, probably not a very good explanation, but yeah.
Thanks. James, there's one more question from Attilio. Great stuff, James. Do you think there's a scenario use case where you can consider Flink over KStream or ksqlDB?
Yeah,
Hello?
look, I mean, oh, sorry.
Sorry, Indrajit, you go for it.
Yeah, I didn't get that co-partitioning clearly what you mentioned. Like, just say, I know that partitioning, but co-partitioning, they say that it has to do the marriage between your K-stream and K-table. K-table concept work in a different way, K-stream work in a different way. And they say that it need to have the same partitioning in K-table and K-streaming. Then how co-partitioning work? I did get, even I watched that video on the Confluent. By definition, it is good. But when I try to replicate in thinking term, I'm not able to replicate that properly. Then could you send some detail on that side?
Yeah, sure. Look, I mean, probably best as a follow-up kind of like link, but like the general idea is that if I want to join data on a key, the data has to be partitioned by that key so that it's co-partitioned, so that the two partitions I'm joining exist in the same space so that we're not going over the network. Yep. But yeah, look, I'll send through a follow-up with that.
Cool. Sorry, James, that last question was use cases or scenarios where you consider Flink over KStreams and ksqlDB.
Yeah, look, yeah, there's certainly, like what we sometimes find is that is just the technology that people prefer, like they've been using it in other applications, and so they're familiar with it. And so it works with Kafka. Like there's, lots of people using kind of like Flink. I can't really talk to the product strengths of Flink. One of the kind of like, I suppose, just the warnings, although I know that it does deal with that, ksqlDB and KStreams are really built with the assumption that Kafka is the source of everything. And so there's some interesting things that allows KStreams and ksqlDB to do, which includes using state within Kafka in interesting ways. So the way that KStream stores state, it actually backs it up with a Kafka topic so that you have durability even in the case where you lose maybe in memory state. And that's really important for kind of like rebalancing and durability. But there's a lot of nuances to that. But if we have customers who use Flink because that's what they've been doing for years and they love it. And so that's fine. So jumping into the environment. So I'm just basically going through to this environment for loyalty here. And let's see, we've got about 10 minutes. So like I can probably do this. So this may start as kind of like a data exploration. We sort of like touched upon the idea of data mesh, and I'm sure it's something that you've been discussing as a group. This idea of a data catalog or, self-service discoverability. So I might start by just like looking up any resources in my organization that relate to loyalty. And here I see sort of like global loyalty events that's part of this kind of like Terraform environment. So that's what I want. And so what I'm doing now is I'm going through and I'm seeing one of these dotted lines, right? This is a topic for global loyalty events. Now, this loyalty events, they will have kind of like schema associated with them, and they'll have this idea of kind of like tagging, so we can actually discover you know, who is responsible for this data stream and how it works. But we may also want to understand where it sits in terms of that integration. Like where is this data coming from? How is it being used? How is it being transformed? And so for that, we can move from the loyalty events into this view called stream lineage. And so in a stream lineage view, I can now see, okay, well, this data is actually being produced by a producer. It's coming through this ksqlDB query, which we're about to have a look at. And then this is the topic that I was looking at. And then I can see that it branches off. And so on one side, it goes to DynamoDB. And so we can actually inspect that and we can see, yep, it's running and it's, you know, it's got traffic going through, and I can have a look at it in more depth. And then it also goes into this other ksqlDB query and kind of like that's pushing data through, etc. And so this stream lineage is kind of like a really useful way of understanding what can become quite a complex topology. And we can even sort of like, you know, that's what's been passing in the last 10 minutes. But if I want to take a 24-hour view, we start to see a bit more of this sort of like, I suppose, complexity. And this is actually, these three data sources represent the fast, slow, and batch data that I was talking about. So one of these is a CSV. One of these is a database integrating via CDC. And the third one is actually just fast moving data. And I can see that my topology is kind of like joining this data, and various things are happening with this data, which is all interesting, but like, let's get to the ksqlDB. So if I go back to the cluster and I actually have a look at a running ksqlDB application, you can see here that this is sort of like very accessible, because you can just go in via an editor. But we can also see the sort of like the flow of the topology. And so this probably is more aligned to what I drew out initially, where we have this credit raw, which is coming off a CSV. And I can sort of like click on that credit raw topic and I can see the kind of information that is coming in. Okay, so that's basically coming in from a CSV. And if there's time, we can look at the CSV. There probably won't be. The customers raw is interesting because this is coming in via CDC. And so if I take a look at the data, the shape of the data coming in, it's a very sort of CDC-centric data format. So we've got this idea of before, after, and metadata about how it was generated. All very useful for understanding this data, but not really great for sharing across maybe a domain boundary. So the first thing I might want to do is clean up the structure of this data. So I go from customers raw to global customers, which is kind of a shaped data that can be shared across those boundaries. And so here we see the same data, but represented in quite a different way, where the structure is now a simple JSON object, and we've got a sub-object for address. And the way we did that was using ksqlDB. So having a look in the middle here, we can see this is always fraught with danger, increasing the font size, but we can see this is the query that is actually leading to that change. Now, there are going to be elements to this that you're not familiar with, but there'll also be a general familiarity here where, okay, I'm actually selecting things, I'm using functions to cast things as strings, I'm diving into an object and selecting out some of the nested properties. So a lot of those things are kind of like, well, probably familiar. There are things that will be new as well. And so actually, based on that, like just that co-partitioning, you'll notice that I'm actually partitioning by my customer ID. And that is very much like the conversation we were just having, which is saying that this information, I want this actually partitioned by customer ID because I'm going to be joining on customer ID. And so that's just an interesting kind of like implementation of what we were actually discussing. And so what we've seen there is kind of like, and I'll just return to normal zoom. And then we've got our loyalty events. And these loyalty events are coming through very quickly. And I'll just pause those and we can actually take a look at one. So what we have is kind of like this transaction ID. We have a customer ID, the points and the vendor. But you'll notice we've got a customer ID, which obviously links to my customer here. Like, so that's what we're going to be joining on. But at the moment, my loyalty events are essentially, unenriched. So they're simple. Now, the next state, and so we've sort of like done this create stream, don't have time to go into what that is, but this create table means we're creating a stateful view on top of this stream. And so we've got these 3 stateful views, and it's probably most interesting in the loyalty events. Because these loyalty events, when we start applying state to them, you'll start to see what the kinds of things that we can do. So now we have the same loyalty event. So it's got a customer ID and it's got some points for the transaction, vendor, transaction ID, but we're also calculating the total points for this customer over the life of that stream and the average points per transaction for that customer. And so we're mixing now kind of like a bit of stateful information in here, like, over an aggregate. We're also sort of like, I suppose, what this called materializing a view. We're doing that for each of these topics in preparation for this join. And so this join is kind of like where we take the 3 streams of data and we combine them into one stateful view of a customer. And so when we get here, what we'll see is we have a more complex object, and you'll probably be able to see the bits that come from the different data sources. So here we have kind of like all of that information that is being pulled from the customer profile database. Here we see kind of like the information that is actually coming out of my fast moving data, the point of sale, with some stateful aggregations. Things like my latest loyalty transaction is very kind of stateful, but can be very useful for downstream systems. And then finally, we've got this credit rating, which is kind of like coming through from this batch data. The beauty of this is if we get kind of like a new event in any of these streams, this topology, and particularly this kind of like this create table, which we can see here is basically a join. So you're seeing kind of like the join semantics here. Any of these things change will update the state of the object here. And so in this example, if we were to look back at the stream lineage, you will probably notice that there is a data sync, which is connecting here, and that's going down to a local instance of MongoDB. And so if I was to go to the MongoDB instance, what we would see is we have kind of like all of these objects that are being stored statefully in MongoDB. Whenever there's an update to the upstream system, whether that be a CSV, a database, or that point of sale transaction, that will get pushed down to MongoDB, and MongoDB will basically perform an upsert on the record so that that we actually see kind of like these refreshing. This, I don't think that they've had a loyalty transaction yet. It's relatively new, this system, but you can see kind of like these ones have, Woolworths and Virgin Airlines. And if I was to kind of refresh this page, we might see, we might not, but we might see that one of these transactions has actually changed. So that third transaction is now IGA because there's been an IGA transaction. So the rest of the object has stayed the same, except that this has probably been incremented as well, the total points, and the average points may have changed slightly. So that's kind of like a really quick overview with 2 minutes left. I'll stop there and see if we've kind of like, if that made sense, and if there are kind of any questions coming out of that.
We have good stuff from Greg. Any questions?
Thank you,
team? Okay, I'll probably get started with the question. So master data and reference data use cases for Confluent? Maybe articulate what's the common patterns and use cases.
Yeah, well, master data kind of like it's a really interesting area because when you start to look at these stateful aggregations that can be kept up to date in real time from various systems, kind of challenges some of the sort of like that whole master data management, because a lot of this can actually be done using event streaming and event sourcing. So yeah, like, I mean, in terms of like the canonical view of a business object, we would argue that that can actually be done through event streaming. In terms of kind of like some of the more metadata management, so things that like you'd normally do in Calibra or Elation, or that kind of tool, we integrate with other governance tools via kind of an API, and we've got a GraphQL API against our data catalog. But the issue of managing kind of like schema and stream lineage, and basically managing an event stream system from a governance point of view and from a master data point of view, is quite different. And so like some of the more traditional tools are very good at data at rest, but data in motion is more problematic. So yeah, probably a non-answer, but yeah.
Okay, James, I've got a question. Well, Atalio said, I've seen companies being somewhat concerned with the use of log compaction. Is this something you've applied frequently?
Yeah. So like, I mean, so log compaction is essentially, if you imagine each one of those lines is a log, and I said that we could store that infinitely. Now that sometimes that may not be considered sort of like desirable for whatever reason. So there are different ways you can clean up the log. You can clean up the log just based on date retention. So it might be 7 days. After 7 days, you start to lose events from the tail of the log. But you can also do what's called compaction, which means that at like regular intervals, Kafka will look at all of the events in a particular topic, and it will look for duplicate keys. So an event in Kafka has a key and a value, a few other things. But the key is really important for log compaction because it will only store the most recent version of a key. So it will delete earlier events. And so sometimes, particularly with sort of like a materialized view, where we're actually storing the latest view of a key, log compaction is actually a really suitable technology because we don't need the earlier versions. If we ever have to rebuild, we can go back to the original stream, which can be retained for longer.
Cool. Thanks, James. Any other questions? Oh, so Nitin said in ksqlDB, storage and compute are decoupled from each other. That's the question.
So probably the important thing to note is kind of like, Kafka is the central system, and there are systems that sit around in clusters. So ksqlDB is sort of like a horizontally scalable system that hangs off Kafka. ksqlDB can basically be expanded to the number of partitions in a Kafka topic. When I was referring to the separation of storage and compute, that was specifically around Kafka. So what that means is we have kind of like a layer of what we call hot or fast storage, and then we've got a layer of warm storage. Hot storage is basically on the disks, so it's mounted on the computer, so it's very quick to access, and that's where the most recent events sit. But then over time, they move to object store, which is warm storage. Very efficient because of the nature of the way Kafka just sequentially reads. We can really efficiently prefetch objects. And ksqlDB sits on top of Kafka and uses Kafka. So it also enjoys, I guess, in terms of the way it stores the events it generates, it enjoys that separation of compute and storage. ksqlDB itself will be running as a process, and that will be kind of like a Java process with a heap. And so it will have memory associated with it. It will also have disk storage associated with the instance. And that will scale out with the number of instances. So yeah,
James, just a quick question. So it could work. So ksqlDB horizontally can work on warm and hot storage. Is that right?
Yeah, and like from ksqlDB's perspective, it's unaware of where it's coming from. It's just subscribing to Kafka topics. The topic itself is what sort of like sits on hot and warm storage. So ksqlDB itself, it runs kind of like essentially a key value store in memory. It persists that to local disk, and then it persists that to a topic, which is then distributed across the system. So there's 3 levels of kind of like storage in ksqlDB, and that is there to basically enable performance, but at the same time allow the system to recover in a distributed way, so that if we have to kill an instance and spin something else up, the state is actually stored in a topic, so it's very it's much quicker to actually rebuild the state.
Yes, just to add on this question. So is there any whenever we create the final view to pull the record and to optimize the performance, is there any way to store all the record or topics in a columnar fashions? So like the new NoSQL databases are coming into the picture. So most of the pretty efficient, So
yeah, and that's exactly kind of like, I mean, so you'll see in sort of like 2 cases where I'm actually kind of like pushing this off to an external kind of like data source. So these are downstream systems. And so the first one, which I kind of showed, was that this is actually a MongoDB connector. And so that's where we actually saw MongoDB. So that's an external system that is just grabbing the data that it's concerned with, and it's optimized for whatever it is that application wants to do. So it's very easy, and we can see kind of like, with the other example, which is the DynamoDB sync connector. I mean, that's pushing through to DynamoDB, and that's actually just fully managed. So you can see here that this has just been running. It's kind of like, it's processing messages. We can set the settings there, and if we want to create kind of like a new connector, we can create lots of different connectors via the UI. This is getting a bit into Confluent, but like the general idea is that connectors are just part of the ecosystem, and if you want to push into a NoSQL database or a GraphQL, a graph database, it's just like finding the right connector.
James, very quick question: Oracle and CDC, is that possible?
Yeah, absolutely. Yeah. So Oracle, there's a couple of ways you can do that. So if your customer has a Golden Gate license for big data, they actually offer CDC through Golden Gate. That's quite a pricey license. There are also Oracle CDC connector that Confluent provides that doesn't require the Golden Gate licensing. So it goes through the LogMiner API, and that works very efficiently as a CDC kind of like as a CDC source as well. Yeah.
Got it. Thanks, James. Maybe any other questions from the audience? James, I guess just 2 questions. How would you start, I guess, with this? Yeah.
That is a great question. And the way I would start is by going to developer.confluent.io. And so this is a really, really great source for how Kafka works. But the really nice thing is it has essentially these kind of like these 101s for creating these data pipelines. That's not what I was looking for. It's the, let's see, top use cases. So this is a really good resource because it shows you the different types of things that people are doing in ksqlDB. So these are simplified versions of things that people are actually doing in production. And if you click through to one of these resources, it will actually give you a link to just launch that in Confluent Cloud. And so that will take you into a guided tutorial in Confluent Cloud. Confluent Cloud itself is available without credit card. You can sign up for it. You get $400 credit. You get 30 days to use that credit. There's no credit card required up front. If you wanted to keep using it, then you would be required to sort of like, put in a credit card. But that gives you an opportunity to have 30 days of a fully fledged environment to play around with. If you're more sort of like technically savvy, you can actually download Confluent Platform. You can download Confluent Platform as a Docker image, and that will include ksqlDB as part of that. So you can set that up yourself.
Cool. Thank you, James.
No problem.
Awesome. Rosaline, did you want to wrap up?
Yep, I can. So thank you to everyone that stayed to the end and James's team for co-hosting the event with us. The Zoom has been recorded and we'll be sharing the link on the Meetup as well as our YouTube account.
Cool. And a big thanks to James and the team from dataengine and also from NZ DataOps for myself. Just a quick thing, dataengine's hiring for data engineers, data architects, data consultants. So anyone's keen or interested, just reach out to me directly. Otherwise, James, I guess the other question I had is any questions or any engagements, could we share your email through the Meetup website? Is that okay?
Yeah, absolutely fine. That'd be great. Yeah, and my LinkedIn, I can share that as well. Yep.
Perfect. Thank you. Awesome. Thanks,
Cool.
team. Thanks, James.
All
Thanks,
right.
everyone. See everyone.
See everyone.
Thank you.